Okay, everybody, could you see my screen?
Yes.
Yes.
Yeah, so this is the class quiz that you took last week. um, the midterm exam too, the grading is almost ready. I mean, any time today, you can know the grade for the midterm exam too. Yeah, I will notify you maybe around noon or maybe a little bit late. Yeah, but definitely for sure today you can know the grade for midterm too. And this class quiz has not been graded yet, completed, but I already uploaded the solution for the class quiz and midterm exam too on eCoursera. If you see that exam tab, then you can see the solution for midterm exam too. And if you click on the class quiz tab, then you can see solution. Anyway, so briefly, so everybody remembered this was the problem one for the quiz. If the square waveform shown in figure 1, this means this one, is applied to the circuit in figure 1b, this was the circuit, then find the Fourier series for V naught. So you have to find out V naught for this circuit, provided that this is the input here. So this means that first you need to apply the Fourier techniques on this signal and then apply their latter here. And you can easily find out the voltage, find out the total current multiplied by this impedance. So everybody see the first what I am doing, I am finding those three A naught, then N, and then Bn. Here the total time period is 2. So I am writing omega naught 2 pi over T, which is pi. And then I wrote omega n for nth term or nth harmonic. Omega n is n omega naught, which is n pi. And then I am writing down that equation, and you see, this is the total time period, but function value is 5 between 0 and 1. And function value is 0 between 1 and 2. So that's why you see, I am not integrating or writing down even this portion, because here the value is 0, but here the value is 5. So I just put function of dt, so 5 dt. So ultimately after integrating 5 by 2, and your n becoming 0, because this is cos n phi t. After integrating, it will be sine n phi t. And once you will be putting the limits, then sine n phi, those will be 0. So ultimately n 0. But Bn has value. Vn has 10 over n phi when n is what, and Vn is 0 when n is even. So therefore, once you get that a naught, n 0, and Bn this value, then you write down the general expression. Vst is 5 over t. This means this is the DC quantity, DC voltage, plus this 10 over 5, this one, and then 1 over n, I am writing here, sine n pi t. And then I put the limit in terms of k. K is 1 to infinity, meaning that n value is 2k minus 1. So I think everybody were able to apply the Fourier techniques, right? Did you all get the same result, same value for the quiz? A naught 5 by 2 n 0, and Vn value is like this, 10 over n pi if n is what, or it will be 0 if n is even. So I'm assuming that you all got this one, and then this is your function. And now you see how we can apply for that circuit. So this means now this is the input here. So here you see, first I'm writing that V naught expression in terms of phasor quantity. So V naught is Vs over this one plus this one j omega n. So and then j omega n means j n pi. Because the value is 1, so j omega L, so L value is 1, so you cannot see that 1. So j omega n means j n pi. And this is the current, and then multiply by this impedance, j omega n, meaning that j n pi. So now this is my voltage expression. Now I apply twice. If Vs is this one, 5 over 2, then what is V naught? So meaning that your N value is 0. For DC, N value is 0. So ultimately you are getting 0, V naught. Or if you think from the DC circuit standpoint that your Vs is 5 by 2 DC voltage, then because this is inductor, inductor will be short circuited. Consequently, the voltage across this inductor is 0. So I have written that for DC, VL is 0. So either you understand that way, or in this equation, you put N value 0, then still that is the 0. So therefore we got that one. Now you apply this one. Now this is your function, like 10 over n pi sine n pi t. So therefore, you see, I am writing for Vs that 10 over n pi sine n pi t. I am converting into cosine. Therefore, cosine n pi t minus 90 degree. So it will be the same value. The goal is that I can express this on in phasor form or polar form 10 over n pi at an angle minus 90 degree.
Dr. Lee, can you go back? How did you get the 2K minus 1? Because I ended up getting, I don't know, it's probably just my math, but I got like 2K minus 5. Everything else agrees before that.
Did you get this thing? Vn, did you notice?
Yeah, I got BN and I got those values for BN.
Okay, so after that you see, because you will be getting 10 over n pi only when
Mm-hmm.
n is what?
Odd.
Yes, not for an even, because if you look this one, if n value is 0, 2, 4, then always you'll be getting plus on here. So 1 minus 1, that will be 0. That's why I have written that Vn is 0 when n is even. And if you look, the n value is what, like 1, 3, 5, then see, always you will be getting minus on here, right? Therefore, this minus on minus, it will be plus. So 1 plus on it will be 2. So then it will be 10 over n. Did you get this one?
Yeah, I got that. I just didn't for N,
Okay.
or you got 2K minus 1 and I
Yeah.
got 2K minus 5.
No, it should not be. So therefore, you see here, I wrote, it depends on then how you wrote. You see, here I am writing 10 over 5, exactly this thing, and I took n over n here. Then if you write n equal to 2k minus 1, for example, k value is 1. So therefore, your n value is 1, right?
Right.
And if k value is 2, then your n value is 3. So in that way, if k value is 3, then n value is 5. Because only when n is odd, only then this is applicable.
Okay.
You see? So if
Yeah, I see. Okay. Well, I got that wrong, but I mean, I guess I can get error carried forward.
yeah, probably here you have different thing, or you calculated differently. That's why you got 2k minus 5. I don't know. Okay, so but it's still that quiz has not been graded or looked at. So we'll be looking at that where you made mistake. And then are you fine with rest of the stuff that I am discussing now? This part? Priscilla,
Yeah.
yeah. Did you properly do like that?
Well, I had VS equal to, yeah, it looks like
I mean,
I
this will be the last result. This will be the V naught, the final result. It will look like that, like 10 over root over 1 plus n square phi square, and then sum k1 to infinity cosine of
yeah,
n pi t minus tan inverse n pi, where n is 2k minus 1.
right. So I mean, I have something similar, like it's set up similar, but the number, the coefficient in front of it's different. So
Okay, got it. Yeah. Okay, we'll be looking. Okay, so everybody say, I think I talked about this. I expressed this on in phasor form, and then again I am plugging this number, you see, Vs, this one here. So my V naught for Vs, this one, 10 over n pi angle, this one, and j n pi, I wrote n pi at an angle of 90. That is the meaning of j n pi. And then in the denominator, on plus j n pi, so magnitude is root over 1 square plus n square pi square. And angle is tan inverse n pi over 1, just tan inverse n pi. So then what I am getting, n pi cancel, plus 90 minus 90 angle is 0. So I am getting only 10 in the numerator. And denominator, this one, root over 1 plus n square pi square. I am taking this angle in the numerator. That's why minus tan inverse n pi. Now this is your function. And you know that first part for Vs 5 by 2, it is 0. So that's why I did not write that one. Directly or in time domain, V naught t, this is your magnitude. And because there is n involved, so I'm putting the limit in terms of k. K is 1 to infinity. Because n was the word, that's why n is 2k minus 1. And from here, cosine of n pi t minus, this is the angle. Everybody, did you do in this way? Did you get the same result or you get different result?
That's what I got.
You got that one?
Yes.
Okay, great. Yeah. Hello, Brad.
Yes, sir.
Okay, so was it like that? Similar?
Yes, sir.
Okay. So therefore, everybody see, as I mentioned, I already, actually last night, I already posted this on eCourseWare. If you click that where I uploaded class quiz, under the same tab, you can see this one. So you see, or again, after the class, you look, already I did, yeah. Okay, so the next one, the voltage across the terminal of a circuit is Vt, 30 plus 20 cosine of 60 pi t plus 45 degree plus 10 cosine of 120 pi t minus 45 degree volt. If the current entering the terminal at higher potential is It, 6 plus 4 cosine of 60 pi t plus 10 degree minus 2 cosine 120 pi t minus 60 degree ampere, then find out the average power absorbed by the circuit. This is the question. So therefore, everybody see, I am just writing two values side by side. Voltage expression here, and then at the bottom, I am writing It, so that I can compare component by component. So therefore, then average power, this is DC quantity, this is DC quantity. So in case of average, VDC multiplied by IDC, that is the power. And then you have to compare, you see, 60 pi t, 60 pi t, meaning that they have the same frequency. Here you see, 120 pi t, 120, they have the same frequency. If you have other terms, much more terms, you will just compare component by component. I mean, for example, it is written in that way, but it does not match with the frequency, then you cannot compare with this one. You have to look, you have that similar component or not. That is the meaning. Okay, therefore, for second term, for 60 pi t, half, because I am doing average and I am directly using those magnitude, peak values, that's why I have to use half. So half 20 multiplied by 4, then cosine of voltage angle minus current angle, you see, 45 minus 10 degree, plus for this term, have 10, this is minus 2, cosine of voltage angle minus 45 minus 60 degree. Voltage angle minus current angle, that is the formula. And then if you just put 203.1 watt, this should be the result. Everybody, could you follow me? Did you all get this number or you got different thing?
I got that.
Okay, okay. Julian?
Yeah, I got that.
Okay, okay. So everybody please see, and I already posted. Look, yeah. So now hopefully by tomorrow you might know the grade for this one, but for sure today you will know the grade for midterm exam 2. So now I am showing you that midterm exam 2 solution. Just a moment.
Wait, hey, Dr. Ali, I have a quick question about that second one where you said earlier, like if they had different frequencies, like, so if that were to happen, like on another test or quiz, like what would would we just have to just say we can't solve it, or what exactly do we do?
For example, if this does not match, just an example. For example, here 120, but here you see like 250, just an example, meaning that it is not matching. So this means this term is not matching with any of the frequencies for IT. So this means for IT is 0 for that frequency. So therefore that will be straightforward 0 here because it is multiplication. So for example, write this example. It was like -2 cosine 140 instead of 120, 140 or 130, different frequency. Then even though you start writing that half 10, but ultimately current portion, it would be 0 here. Or with respect to current, there is no voltage component, same frequency, so that would be 0. So therefore, if it does not match with anything, then straightforward, you put that on 0.
Okay, thank you.
Yeah, got it? Yeah. Therefore, typically when problems are given, in most cases, it matches. But if you don't see that or it does not match with the frequency, then that will be straightforward 0. That is the meaning. Okay, great. So now let's open the other one. Everybody, now can you see midterm exam 2?
Yes.
Okay. You see, so this was for you took like about 2 weeks, more than 2 weeks before. You might have forgot the questions, but this was the question. First question was, if IST e to the power -2t ut ampere in the following circuit, then find the value of I naught t by using the Laplace transform technique. So everybody say this was your circuit, IST, and then 1 Henry, 2 ohm, and 0.5 farad. All three were in parallel, and I naught current was entering. You have to find out this current. So first, because you are asked to find out with the help of Laplace transform, first you write down the Laplace equivalent circuit. So that first I am doing. This is the Laplace equivalent circuit. So 1 over 1 plus st, because it was e to the power -2t. This is, j omega L. So s equal to j omega, just s. This is 2, and this is 1 over j omega c. So j omega is s, so 0.5, so 10 over 5, 2 over s. And I gave this name I naught s. And I am defining a new name of the current here, I1 s. It was not in the circuit. I just defined this name. I'm assuming here the current is I1 s. You might give different name, no problem. So how I did, you see that handwritten calculation, how I did, first I made, because this is the total current, 1 over s plus 2. First I find out how much current is going here. And then I am finding out next time, this is my total current. Based on that total current, how much is going through this one. And then if you know this current multiplied by 2 over s, that will give you your voltage here. Oh, sorry, you just need to find out the current. Sorry, that's all. So therefore, what I am doing, everybody see, first I am making the equivalent of these two, rightmost two component, 2 and 2 over s. So that's why I wrote that on G prime impedance, 2 multiplied by 2 over s divided by 2 plus 2 by s. So I got 2 over s plus 1. I did that one, meaning that the parallel combination of these two is this one. So why I did that? Now I got two parallel branch. One is this one S, and the other one is that parallel combination, which is this one, 2 over S1. So everybody assume that 2 over S1 is here, that is one branch, and this is the other branch. And now your total current is going at this point 1 over S plus 2. Then find out how much is going to that combination, parallel combination, which is 2 over S1. That I am doing it here. That ionize is total current multiplied by this one is over S plus that one that I got 2 over S plus 1. And then I got that on ionis. And once I got ionis here, then now this is your total current. Find out this current. So meaning that this current is, according to current divider rule, this current is total current multiplied by 2 over 2 plus this one, 2 over 2 by S. That I am doing. So you see, ultimately I got in that format S square over S plus 2 and then S square plus S plus 2, and then I am applying partial fraction. Then finally I got this format, and this is my result. So everybody see, this should be the result. I naught t e to the power minus 2t minus 2 over roots over 7 multiplied by e to the power minus half t, then sine of root over 7 by 2t, then ut. Did you all get this result? So if you have your hard copies that you submitted, that you uploaded on the exam day, then you can compare that you got this thing or not. But everybody, could you follow the process?
I think I made it to the part with the partial fractions, and then after that, it kind of fell apart for me.
Okay. Got it. Yeah. So therefore, I just use, the simple thing, the basic algebra, partial fraction. I said, okay, this one is a over s plus 2 plus bs plus c over this one, because there is s squared. And then I'm equating the term for s squared, s, and then coefficient. And I got three equations. My b value is 0, a value is 1, and c value is minus 1. And then I got this one, 1 over s plus 2. Here, as you can see, s squared plus s plus 2. You can write s plus half whole square. But then here you are getting 1 by 4th, but here it is 2. So therefore remaining is 7 over 4. So that's why I'm writing root over 7 by 2, then square. And then if you put root over 7 by 2, then this represents that sine function. But then because you are putting in the numerator, this is additional, so you have to balance by writing 2 over root 7. So then the value will be the same. Is everybody fine? Does anybody have any question, comment? So I'm assuming everybody is fine. For this one, given the following transfer function, realize the function using the circuit in figure to select R equal to 1 kilo ohm and determine the values of L and C. So this is the circuit. This is the transfer function, V2 over V1, voltage across capacitor over the input voltage, which is this one. Now find out L and C. So therefore, what I am doing, first I am making the total impedance from this circuit. First I am making the total impedance here, GT, and by putting S equal to J omega, that I am doing. And then I am finding total current here. Once I get the total current here, then I am applying the current divider rule to get the current here. And then I am multiplying that current by the impedance of C. That I am doing. So you see my calculation, everybody, IT, then IC, and then I got V2 this one, and V2 over V1, this should be the expression. V2 over V1 in the numerator, S over RC, and in the denominator, S square plus S multiplied by 1 over RC plus 1 over LC. And then this is your function. Now you compare with this one, given function. So therefore with S, it is 2. So, and then this one is 6, and this one is 2S. So therefore, if you compare the numerator, so 1 over RC, which is 2. So therefore, your 1 over RC is 2. Or in other words, I think I wrote 1 over LC is 6, this one. 1 over LC, which is 6, and then L, this one. And then I wrote that on 1 over RC is 2. R value is given, my C value is 0.5 millifarad, and then L value is 333.33 Henry. So therefore, these two are the answer. C value 0.5 or half millifarad, and N value is this. Did you all get the same number?
Yes, I got that.
Okay.
Yes.
Yeah. So everybody see, like I did it here. I already uploaded under the eCode set this solution. So you look, you match with your solution, and then today you can see your grade. Okay. So then question number 3. In an RLC circuit, R value is 20 ohm, L is 4 Henry, and C is 1 farad. The circuit is magnitude scaled by 10 and frequency scaled by 10 to the power 5. Then calculate the new values of the elements. This means this is magnitude scaling and frequency scaling that we learned in frequency response chapter. So in this case, magnitude scale by 10 means magnitude scale factor, Kf is 10. Frequency scale by 10 to the power 5 means this is Kf, frequency scale factor. So this is Km, this is Kf. And then based on that, these are your original values. What should be the new scale values? That is the meaning. So that I am doing it here, I wrote Km10, Kf10 to the power 5, based on this information, this one and this one. And then those three values are given, RLC. I am writing generalized equation. New value, R prime is K multiplied by R. This is my Km, this is my R, 200 ohm. L prime is Km over K multiplied by L. Then I am getting 0.4 millifarad. And then C prime is C over Kf Km. I am getting 1 microfarad. That is the answer. So, is everybody fine? Did you all get this thing?
Yes.
Okay, yeah. So everybody, after the class, even you see and you match with your answer. Okay, the number 4, an auto transformer with a 40% tap is applied by a 400 volt 60 hertz source and used for step down operation. A 5 kVA load operating at unity power factor is connected to the secondary terminals. Find a secondary voltage, the secondary current, the primary current. These are the questions. So first you see, everybody, I have drawn a diagram for your understanding. Assume that auto transformer means the same winding will be shared by the primary and secondary. So in the secondary, there is a tapping, which is that, 40% tap is supplied by 400 volt and is used for step down. So this means that 40% tap is being used for step down. This means the total is, if you say the total is your N on number of turns, then the tapping is at 40%. So secondary turn is that 40% of N on. That's why I have written 0.4 N on. And my applied voltage is 400 volt, which is V on. This is my ion. I have a load connected at this side, secondary side. The value is 5 kVA. Power factor value is 1. And the voltage V2 appears. Here is the current. Now see, I am writing that on V1 over V2 is N1 over N2. My basic equation for transformer. N1 is N1. For N2, I am writing 0.4 N1. So consequently, I am getting V2 is 160 volt. And once I get V2, meaning that this one, I am able to get the current I2 because load value is given 5 kVA. And if I multiply it by that power factor value, it is going 5 kilowatt. So 5 kilowatt over V2, that is my I2. So my I2 is 31.25 ampere. And once I got I2, I know N1 and N2. So I'm writing, you see, I1 over I2 is N2 over N1. The relationship between current and turn ratio of the transformer, this one. And then I am plugging all the numbers. So I got I1 is 12.5 ampere. So I got all three answers here for this one. Did everybody get the same result, these three?
Yes.
Okay, great. Now the last question was, for the following circuit in find V0. Here you have to find V0. This means if you can find out the current for this loop, for this portion, then that current multiplied by 1, that will be your V0. So therefore, you see that once again, I think I wrote down, and then I'm writing down equation for this loop and for this loop. I wrote down, and from 2 I find out the value of I2, which is this one. I substituted I2 in another equation, equation 1, and then I calculated first I got I1 value 1.95 angle minus 69.53 degree ampere, and then I got I2. Finally, the result V0 is 0.54 angle on 44.160 degree. Did you all get this result, this number? V0 final value 0.54 angle on 44 degree on 610 on 6 degree volt. Is everybody fine with this one?
I just got the angle for the current one, and then it looks like I was off on the
I2 is different?
yeah.
Okay. If I2 is different, then you will be getting V0 different. Because basically I2 is the answer for V2, because you know that V0 is just 1 ohm. So if you multiply that current by 1, result will not change. So basically I2 is the answer for V0. So therefore you are much off with I2 than the, so look what mistake you made. If you see this one, and then this angle is going in the numerator, so that is becoming minus. So ultimately here it is minus 35, and then value is minus. So accordingly, first I'm writing V0 is minus, but then if I rotate 180 degree, then this minus will be plus, and here you have to add plus 180 degree. So that will be your this one. So is this fine, Priscilla?
Yes.
Yeah, so therefore look later where you made mistake, which line, if you compare this one. Is everybody fine? Did you all get the same result? So Brad, did you get the same result?
Yes, sir.
Okay. So you all please match. I already uploaded. Okay, so moving forward. Hold on. Now, can you see the class slides? Once again, the reminder about your midterm exam 3 that to be held in next class. I already discussed last class. So the once again, the syllabus starts from class 27 through today. Today, this is the 33. And then again, the question pattern is the same as usual, like midterm exam 1, midterm exam 2. Again, like you will be asked 4 to 5 questions. And here, as you can see, although I mentioned this is that official time, but you can submit until 12, until noon. So therefore you can start at 8 to until, that is the last time. So therefore, as I always recommend you, you try to finish writing around 11 and then you jump into the scanning and converting PDF and uploading. So then you will be fully fine. Okay, so now everybody see, we were discussing that three-phase circuit. You understood something, the delta Y configuration, the voltage current relationship, power calculation, etc. Today we will be looking on, again on or two examples, and then we will be done. One important thing in the three-phase circuit, you notice the phase sequence. And I have written positive and negative. So what does that mean? This phase sequence is related to that three-phase system, three-phase balanced system. So here everybody see there are two figures on the left side, as you can see, Vn, then Vbn, then Vcn. That I explained, which is called the ABC or the positive sequence. This means first FH, then phase B, 120 degree, then phase C. On the other hand, look the right side this one, first phase E, then phase C. So therefore, the difference between phase A and phase C, that minus 120 degree clockwise, then phase B. So therefore, I mean, this is three phase, this is three phase, but here the sequence is A, C, B. So therefore, with respect to this positive sequence, ACB is called the negative sequence. So therefore, it's just a matter, now if you look these things, like when it is ABC phase sequence, what is the meaning? Meaning that phase A will come first, then after 120 degree phase B, then after 120 degree phase C. If you really look the waveform for three phase through the oscilloscope, then you will notice this one. The first A phase, then B phase, C phase. Accordingly, it is called ABC. And then you look this one, bottom one, everybody. A, then C, then B. A, C, B. In that way it is going on. This is which is this one. So this is called the negative sequence with respect to this one. Now what is the meaning of this one? I mean, all over the world, these two sequences are followed. I mean, most of the countries follows this on ABC phase sequence, but some countries follows this on ACB sequence. This means it depends on how they structure the coil on the generator, on the power plant. They put first FH coil, and then they put 120 degree apart C phase coil, and then 120 degree. That's why it is the ACB. Now, there is no problem in those countries that follows the ACB. But the problem is that, for example, there is the significance or importance of these two. For example, you purchase a device from a company of some other country that has ACB phase sequence, three-phase device, and then this is your system. And then you are trying to connect to your system, but your system has that ABC sequence. Therefore, see, when you are connecting, you are matching, you are connecting FH with FH. This is fine. But then you thought that, okay, I am going clockwise on 20 degree. I am going clockwise on 20 degree. Let's connect this phase to this phase. But you see, this is problematic. This is C phase here, but this is B phase here. And then here it is B phase, but then here it is C phase. So therefore, when you will be connecting FH, FH, that is fine. But once you will connect this one to this one, then that is problematic. What will happen, for example, you have a three-phase motor in an industry, and that was rotating, your motor was rotating in a clockwise direction. Once you connect this thing, then motor will start rotating in the reverse direction. That is problematic. So once you notice, then immediately you stop the system, meaning that your phase sequence is not matching. That is the problem. So that's why you don't need to go further beyond this thing. You just remember that there are two types of phase sequence in the three-phase system. One is called ABC, other is called the ACB. So meaning that in the numerical problem, if it is mentioned, okay, you have a three-phase system and that three-phase system has ACB sequence, then immediately you have to write down that Vn is 0, then you have to say Vcn is minus 120, and Vbn is that plus 120. And then accordingly, you have to solve the problem. So everybody, could you follow me what I said?
Yeah.
Yeah, it is just a matter of like which phase comes first and then which one is next. Yeah, it in United States, this is the sequence ABC in United States, but some other countries so may have this on ACB. So that is the thing I am telling, that you purchase a device from those country three-phase and you are trying to connect to your system, that time there will cause some problem. There will be some issue in connecting. As I gave you an example that if it is motor, it will start rotating in the reverse direction, which is not desired. Okay, so therefore now moving forward, some numerical example. Everybody see this one, this example. Let me a little bit bigger. The unbalanced Y load of the following figure has balanced voltages of 100 volt and the ACB sequence. You see right now the phase sequence is ACB. It is not ABC. So, and then calculate the line currents and the neutral current. Take G8 15, GB 10 plus J5 and GC 6 minus J8. So therefore everybody see, this is an example of three-phase system, A phase, C phase, and then this is B phase. And this is the neutral line. The figure shows that I current is entering here, IB is here, IC is here. Through the neutral, current is entering in that way. And then voltage are given. This is VN, this is VBN, this is VCN. But it says it is unbalanced. Because it is unbalanced, consequently, GA, GB, GB, GC, all three impedances are different. If you see the magnitude, GA this, GB this, and GC this. Now, based on that, find out the line currents. What is the current here? And the neutral current. How much is flowing through neutral? So therefore, as you can expect, that because this is unbalanced system, so there should be some current flowing through neutral. It is not zero. If it is balanced system, only then the current flowing through the neutral will be zero. But here you might expect some value. Therefore, everybody see the solutions here. First, what I am doing, first I wrote based on ACB sequence because that was given. You see, balance voltage 100 volt, but the ACB sequence. So this means first I am writing VAN, which is 100, but then VBN is plus 100, not minus 120. And then VCN is minus 120. This means this is the ACB sequence. And then accordingly, I am finding IA current, this one, VN over GA, this impedance. So GA is my 15. So I got this one. Accordingly, IB this one, IC this one. You see, in all cases, IA value is different. Even their angle is absolutely different because this is unbalanced system. And then you look, this is the IN. So this means IN is IA plus IB plus IC and then minus sign. Because here in the problem, the indicated direction is here. This is the neutral current. So that's why everybody see, I have written current in the neutral line, IN is minus IA plus IB plus IC, which is the sum of these three. So after Phasor algebra, I got 10.06 angle on 78.4 degree. So everybody, could you follow the problem?
Yeah.
So therefore, I mean, everything is given. Like you say, Vn given, Vbn, Vcn, those things are given. But only thing you have to be careful in giving that angle, Vn, Vbcn. This is based on this on ACB sequence. That is the significance of this on previous slide that I was explaining. That you have to clearly look in the problem. It is mentioned ACB or ABC phase sequence. That is the meaning only. So and then all three impedances have different impedance. Consequently, you are getting different current. And this is Y connected system. Just sum up all those three current and then give the minus sign because ion is in this direction. This is given direction. So then you are done with all line currents and neutral current. Okay, so then moving forward, there is one more problem. It will make you much more clear. Everybody see this example. A three-phase supply with the line voltage of 240 volt RMS positively phased. Positively phased means positive phase sequence. It is expressed in that usually positively phased, meaning that your phase sequence is this one, A, B, C. That is the meaning. Okay, has an unbalanced delta connected load as shown in figure below. This is the delta connected load, but the load is unbalanced. Can you see here 40, here 30, here say 25. Consequently, all current will be different. So then find the phase currents and total complex power. For this case, what are the phase currents and what is the total complex power? But the line voltage is given. Line voltage means line to line between these two lines is 240 volt and they have the positive sequence, meaning that this is, if this is A phase, then B phase will be minus 120, C phase will be plus 120. So everybody see, first I'm writing that on VAB, this on VBC, VCA. You see, A, B, C sequence, minus 120, plus 120. And then I am calculating what is my IAB, VAB, over what is this one, J25. I am getting this one. Similarly, I calculated IVC, ICA. And then, so I got those phase currents and I have to find total complex power for this load. This means because you cannot do at time like root 3 VLIL cos theta because it is unbalanced system. As you can see, current magnitude all are different. Their phase angle are different. So you have to do one phase at a time. So therefore, what I am doing, everybody see, what is my complex power equation? S is VI conjugate for a single phase system. S equal to VI conjugate. So therefore, total complex power, first for phase A, VAB IB conjugate plus VBC IBC conjugate plus VC ICA conjugate. I am doing one phase at a time because this is unbalanced. And then I am plugging, you see, what is VAB? This is my VAB. What is IB conjugate? My IB is here with minus 90 sine angle, but here I am doing plus 90, because it is conjugate, so angle sign will be changed. And same thing I am doing for B phase, C phase. Finally, I got, this is my result. So you can leave in this format or you might express it in polar form, but this should be the result. So I am done. Everybody, could you follow me?
Yes, sir.
Anybody, do you face any difficulty? So here is one important thing. It is mentioned 240 volt RMS positively phased. So positively phased means follow the positive phase sequence, which is this one, that first A phase, then B phase minus 120, then another minus 120 C phase, or in other words, anti-clockwise plus 120. That is the difference between the ABC or ACB phase sequence. So based on that, first I wrote this one. Similarly, in the previous problem, you see, based on the ACB phase sequence, at first I defined those voltage. The phase sequence will determine your proper sign and which phase is coming first. Okay, so you all just look and make practice by using pen and paper and calculator, then you all will be getting. Here now, understand, that will be fine. Okay, that on the last important thing for you for the three-phase system, you see pretty interesting. 2 wattmeter method for three-phase power measurement. So you all know that wattmeter can measure the wattage value, real power, right? So in the lab, you have used voltmeter, ammeter, and wattmeter. Wattmeter measures the real power in a circuit. Now, I am measuring three-phase power. So then it is the expectation that you will have 3 separate meters, wattmeter for one phase, for A phase 1 wattmeter, for B phase another wattmeter, for C phase another wattmeter. So it is the expectation, or it is the guess, that you might need 3 sets of wattmeter to measure three-phase power. But instead of 3 wattmeter, 2 wattmeter is enough. That is pretty interesting. The 2 wattmeter can measure the three-phase power. So that's why you see I have written that to measure the power in a three-phase circuit load, it is conceivable that a wattmeter can be connected to measure the power in a single phase, and this quantity can be multiplied by 3. Or if you not connect 3 wattmeter in 3 circuit, you just measure 1 then multiply by 3. But in most practical circuits, however, it is impossible to connect a wattmeter in this manner. Consequently, a method called the 2 wattmeter is generally used. And the connections for this method are shown in the next slide I am showing. And the algebraic sum of the 2 wattmeter readings is the total three-phase power. So this means that if you just get the reading from 2 wattmeter, and if you just sum those 2 wattmeter reading, that will give your three-phase power. So therefore, everybody see, this is the arrangement. For example, first everybody see, there are three-phase coil. Oh, you see these numbers like H1, H3, H4, these are from a real coil, realistic coil, from on transformer coil. These have been taken, that's why those numbers are given. So you forget this notation. Just this is on coil, C phase coil, this is F phase coil, and this is B phase coil. And now, for example, you have that 3 terminal available, and you want to measure the three-phase power for these 3 coils. So then everybody see how it is done. With the help of 2 wattmeter. W1 means this is 1 wattmeter, W2 means this is another wattmeter. And you all know that wattmeter has 2 coils. One is called current coil, other is called the voltage coil. So this is on coil, because wattmeter, meaning that it will measure the power, which is the multiplication of voltage and current, even without that power factor. So that's why there are 2 coils, voltage coil, current coil. And then you see how the current coil is connected. You see it is connected, for example, for this page in series, because it will measure the current, and always ammeter is connected in series. But then look, voltmeter, one side, one port is connected with this one here, but then the other one is connected. To measure the voltage, you need 2 points. So one point is here, this one, for this coil. You see the connection. But then other point where you will connect it, you see they here, the B phase at this point. See the bold point, dotted point. And then pretty interesting thing, you see, you have another wattmeter. Again, you are connecting the current coil in series with this one, this phase. And then the line is going. But then look, the voltage coil, on end you are connecting with this phase, to which you are measuring the voltage. But then other end of the voltmeter is connected here. So this means that this 2 wattmeter is taking into account all 3 coils, because you see this one, this is on common point. That's why automatically, inherently, it is taking into account all three phases. Therefore, if you just energize the circuit, this is like your three-phase circuit. You see source 208 volt or three-phase 60 hertz, and just on emitter is connected here, just to make sure that how much current is going. If you just energize these three line in the laboratory, then you will get two readings, one reading from this one reading. And if you just sum up those two readings, that will be give you the three-phase total power. So that's why it is called 2 wattmeter method to measure three-phase power. Everybody, could you follow me what I said? So have you used this wattmeter to measure the power in a circuit?
No.
Okay. So this is the wattmeter. So in this case, just what is on the 2 wattmeter is enough to measure the three-phase power. And this is the configuration. So therefore, in this class, in the lab, you don't need this type of arrangement. But in case, in the future, in any time, if you need to measure the three-phase power, then this should be the configuration. That's why I have shown you this diagram, so that it is not surprising to you that why I need 2 wattmeter to measure three-phase power. Why not 3 wattmeter, or why not just using only wattmeter and then multiplying it by 3? Okay, so with that, I will not go beyond this one for the three-phase system. So that's all the syllabus for the midterm exam that will be held after tomorrow, and even for the final exam. So up to this is your syllabus. I think some of you have the next class, so you may proceed. Does anybody have any question, comment?
Is your final exam going to be on the same day as the school calendar?
Yeah, yes. I think I already mentioned in that syllabus. Yeah.
Thank you.
Yeah, I would remind each of you, I think, on Monday, because Monday is your last class, I think, with me for this semester. November 16th is the last class for this course. And on that day, I will remind you about the final exam date. But keep in mind that which is already mentioned in the syllabus and already uploaded. And that syllabus is the university calendar, actually. Okay, so with that, I'm stop sharing here.